One of the biggest headaches for product teams, especially early on, is just how long it takes to get from a digital design to something you can actually hold and test. I mean, you've got this great CAD model, but that first physical part can feel like it's weeks away.
Yeah, it's a classic problem, isn't it? You've poured all that effort into a design and then you hit this wall of waiting. That's actually where rapid prototyping really shines. We're talking about a whole group of techniques that let you quickly make a physical part or assembly directly from that CAD design.
So, it's about speed, right? Like getting that tangible object in your hands much faster. How does it actually do that? Is it just faster machines?
Well, it's not just faster machines, though that helps. The core idea is additive manufacturing. So instead of machining material away, which is subtractive, we're building components layer by layer. Think plastics, resins, or even metals stacked up. You're basically printing a testable model directly from your CAD data, which totally bypasses the need for special tools or molds, at least initially.
Huh? Okay. So, no expensive molds to start with, that makes sense for speed. And I guess that means you can also try out more ideas?
Exactly. That's a huge part of its relevance, reduced development timelines. Designers can get a physical model of a conceptual part in literally hours. Then teams can do geometry tests, check ergonomics, test functionality, all super early in the design cycle. This iterative approach, where you're constantly refining, saves a ton of time that would usually be spent tweaking things much later, closer to mass production.
So, it's not just about getting a prototype, it's about getting many prototypes quickly and cheaply enough to really experiment.
Spot on. You can develop several design revisions in a very limited time frame. It gives engineers the freedom to test various prototypes without having to invest in expensive manufacturing setups for each version. It's a game changer for experimentation.
That makes a lot of sense, especially when you think about complex products. You mentioned it's a critical link between digital design and production now. How has this technology actually evolved? Because I imagine it wasn't always this robust.
Oh no, not at all. The concept really started emerging in the 1980 mells. Engineers were looking for ways to create tangible parts from digital models without needing heavy machining or tooling. Stereolithography, or SLA, was one of the first big breakthroughs. That was using UV lasers to cure liquid polymer resin into solid layers. Pretty neat for the time.
So, curing liquid with a laser, that's where it began. And then what? Did it just get better, or did new methods pop up?
Yeah, new methods definitely popped up. Through the 90s and early 2000s, we saw the development of things like selective laser sintering, fused deposition modeling, and binder jetting processes. Those really expanded the range of materials we could use and increased the reliability of the prototype components. It's been a gradual transformation, blurring the line between a research tool and something capable of low-volume production.
Right, I remember some of those early prototypes. They were mostly for visual models, just to see what it looked like, not really for testing.
You're right. Early on, parts weren't robust or accurate enough for rigorous testing. But material science and machine accuracy have come a long way. Now, we can create durable parts that can actually endure mechanical stress, which is a huge leap.
Okay, so it's building layer by layer, driven by digital design. What are the fundamental principles that make rapid prototyping distinct from, say, traditional machining?
Well, the layer-by-layer fabrication is absolutely number one. As I said, it's additive. We're applying material in successive layers to form the object, not removing it. Those layers are thin cross-sections of the final part, and they accumulate to build the full geometry. You can adjust the thickness of each layer to thinner. Layers mean smoother parts, but they take longer to build.
And that additive method, that's what lets you make those super complex shapes, right? The ones that would be impossible with traditional methods?
Exactly. It opens up a whole new world for complex geometries, internal structures, things that subtractive methods just couldn't touch without huge compromises. Then there's the digital design integration. The entire process starts and relies on a CAD model. Once the design's ready, it's converted into machine-readable instructions. That direct link between software and production equipment cuts out a lot of the usual middle steps.
So, if you need to make a change, you just tweak the CAD file and you're good to go? No retooling?
Precisely. It's digital, so designs are easy to store, modify, and duplicate. Engineers can make rapid changes to dimensions or features and develop new prototypes without having to retool on a large scale. That feeds directly into the next principle, rapid iteration and design testing. The speed means you can test different versions of a product really quickly. You find weak points, refine geometry, optimize performance, all before you're committed to mass production.
So you can test for structural strength, aerodynamics, ergonomics, everything?
Yeah, all of it. Structural strength, aerodynamic efficiency, ergonomic comfort, aesthetic appeal. You can put prototypes through those tests. This ability to switch between design and physical testing is a huge boost to efficiency and drastically reduces the risk of costly design mistakes. And the last core principle is reduced tooling requirements. Traditional manufacturing often needs special molds, dies, or fixtures. Rapid prototyping largely bypasses that. The fabrication is computer controlled, so the same machine can produce entirely new components just by loading a new digital model.
That's a huge cost saver, especially early on. You're not sinking money into tooling that might become obsolete with the next design revision.
Exactly. It's incredibly helpful in those initial development stages when designs are still fluid. Engineers can explore new ideas without having to invest in new tooling every time they make a change.
That's a great overview of the principles. Now, let's get into the specifics. What are some of the common rapid prototyping technologies you see on the shop floor, and what kind of materials do they use?
Sure, we see a lot of fused deposition modeling or FDM. That's where a melted thermoplastic is extruded through a heated nozzle, building up the part. Common materials are ABS, PLA, nylon. It's great for concept models and functional prototypes because it's relatively inexpensive and accessible.
Oh, so like the desktop 3D printers people might be familiar with.
Yeah, that's essentially FDM at its core. Then there's stereolithography, SLA, which we talked about earlier. That's using a UV laser to cure liquid photopolymer resin layer by layer. It's fantastic for high-detail prototypes and medical models because it gives you really smooth surfaces.
So FDM for rough and ready, SLA for detail?
Broadly, yes. Then you've got selective laser sintering, or SLS. That uses a laser to sinter powdered material, typically nylon or other polymer powders, into solid layers. SLS is excellent for functional prototypes and complex geometries because it builds strong parts without needing support structures. For casting molds or low-density prototypes, we might use binder jetting, where a liquid binder selectively joins powder particles, often sand or metal powders. And for really high-resolution prototypes, there's material jetting, which deposits and cures droplets of liquid photopolymer.
Okay, so a good range of options depending on what you need. And speaking of materials, you mentioned plastics, resins, metals. What are the typical materials First Mold works with for these processes?
Well, thermoplastics are very common. Things like ABS, PLA, and nylon. They offer a good balance of durability, affordability, and strength, making them ideal for mechanical tests and working prototypes. Then there are photopolymer resins used in SLA and material jetting. These can produce very fine parts with smooth surfaces, great for visual models and complex components.
Are those resins as strong as the thermoplastics?
Not always. No. Many resins can be more brittle than thermoplastics, so you have to handle them with caution. And increasingly, we're using metal powders in advanced systems. Stainless steel, aluminum alloys, and titanium are used in powder-based processes to create high-performance components for things like aerospace, automotive, and medical industries.
That's a huge jump in capability from simple plastic models to actual metal parts. So, when a client comes to you, how do you decide which material is best?
It really depends on the prototype's purpose. We look at mechanical strength, heat resistance, pliability, and of course, cost. For example, if it's a conceptual prototype just to show appearance, we'd prioritize surface finish and visual accuracy. But if it's a functional prototype for mechanical testing, it needs materials that can withstand stress and repeated use. Nylon or even metal powders would be in play then.
Got it. So, let's say a client has their CAD model and you've selected a material and process. What's the actual workflow? What happens from the digital file to the finished part?
It always starts with the CAD model development, obviously a good 3D model. Engineers design it with parametric tools, defining dimensions, surfaces, structural features. At this stage, you've really got to consider the part's requirements and the limitations of the chosen prototyping process, things like wall thickness, overhangs, internal cavities. Sometimes we run simulations here too, to gauge structural performance before we even fabricate.
So, the CAD model's accuracy is crucial. What happens after that?
Once the CAD model is solid, it has to be converted into a format the rapid prototyping equipment understands. The most common format is an STL file, which describes the geometry surface as a mesh of triangular facets. During this conversion, that digital model gets mapped into thousands of tiny triangles that represent its exterior surfaces. The smoothness of that mesh directly impacts the accuracy of the final prototype.
And if there are errors in the mesh?
Yeah, we have to heal those. Mesh holes, inverted surfaces, non-manifold geometry, any errors like that need to be fixed. That ensures the file is readable by the slicing software and the manufacturing system. Then comes model slicing and toolpath generation. The slicing software takes that 3D geometry and divides it into thin horizontal layers, cross-sections of the final object. This is then translated into machine code that tells the rapid prototyping device exactly how to build each layer.
So, it's like a recipe for the machine.
Exactly. It defines layer thickness, material deposition patterns, support structure positions, machine movements, all of it. This slicing step is critical because it determines the resolution, surface finish, and how long it'll take to build. Adjusting those slicing parameters can significantly affect the quality and structural characteristics of the end product.
And then the machine just makes it?
That's right, prototype fabrication. The machine starts adding layers from the bottom up until the complete geometry is created. The exact mechanism, of course, depends on the technology. FDM heats and extrudes plastic. SLA cures liquid resin with UV light. Powder-based processes use lasers or binders to fuse particles.
And what about those supports you mentioned? The stuff that holds up overhangs?
Yeah, support structure removal is next. Most rapid prototyping technologies need provisional structures to support overhanging parts during fabrication. They prevent deformation or failure. Once the part's built, those supports have to be removed. That might be mechanical extraction, dissolving them in a chemical solution, or just stripping them off by hand. You have to be careful not to damage the delicate features of the prototype during this step.
So the part comes off the machine, supports are gone. Is it ready then? Or does it need more work?
Almost always needs more work. That's post-processing and finishing. Raw prototypes often have visible layer lines or rough surfaces from the layered process. So, techniques like sanding, polishing, painting, surface coating, or even secondary machining might be necessary. Resin-based parts often need additional UV curing to achieve full mechanical strength. These finishing operations really enhance the aesthetic and mechanical characteristics, making the prototype ready for evaluation, testing, or presentation. We can transform a basic prototype into something that looks very close to a final production part.
That's a pretty comprehensive workflow. So, summing all this up, what would you say are the biggest advantages of rapid prototyping, and are there any limitations that product teams should be aware of?
Okay, so advantages first, the huge reduction in product development time. Digital designs can become physical models in hours or days, letting you test ideas incredibly fast. That really speeds up time to market. Second, it lets you create complex geometries with minimal material waste. Additive methods allow for internal structures and intricate details that are really tough with traditional machining. That gives designers a lot more creative freedom. And third, it reduces development costs in those early design stages. No special molds or tooling means companies can develop small quantities of prototypes without a massive upfront capital investment, making it easy to do multiple design cycles.
Those are some compelling benefits, but nothing's perfect, right? What are the downsides or challenges?
You're right, there are always constraints. One is the mechanical performance of some prototype materials. While new systems create strong components, certain materials might not be as strong or heat resistant as parts made with traditional methods like injection molding or metal casting. Then there's surface finish and dimensional accuracy. Layer-based fabrication often leaves visible layer lines, which means extra post-processing to get smooth surfaces. For really tight tolerances, secondary machining might still be needed.
And I imagine it's not the fastest for, say, millions of parts?
Exactly. Speed of production is a constraint for mass manufacturing. Rapid prototyping works exceptionally well for small batch sizes. For large volumes, conventional manufacturing processes are simply more cost-efficient. So really, rapid prototyping isn't a replacement for mass production. It's best used as a complementary technology within the broader manufacturing ecosystem. It supports design validation, product testing, and low-volume production, preparing a design to confidently transition to those mass manufacturing methods. That's where it truly shines.